Today, I'm going to talk about structural equation modeling. So, structural equation modeling, or SEM, is a set of statistical techniques that are used to construct models to depict, measure, and analyze interrelationship amongst observed and latent variables in a multivariate data set. So, it's a rather advanced statistical technique and it examines linear causal relationships amongst variables. So it's looking at the causal relationships between two or more variables, while it's also simultaneously accounting for measurement error. And it's one of the only models that can do all of this at the same time. So it's essentially akin to a path analysis using latent variables. Another way to think of it is just really a combination of a factor analysis and a multiple regression done at one time. So when we think of SEM, we think of the structure of the model. That structure is a system of equations that are usually designed with arrows and symbols, which is known as the path notation. And we think of the equations, which are the mathematical and statistical properties that are implied by the model and its structural features that we then estimate. So some examples for studies for which we would use SEM might be a teacher who hypothesizes that a student's home environment influences their achievement in school, or a healthcare professional who wants to evaluate if a good diet and regular exercise reduce the risk of heart attack. So in these examples, the researcher believes, based on theory and some empirical research, that sets of variables define constructs that are hypothesized to be related in a certain way. So that's in a nutshell what SEM is. But before we go too much further, let's define some terms that I'm going to be talking about today. Latent variables, those are variables that are not directly observable or measured, but rather they're inferred factors that consist of at least two interrelated measure variables. So these variables are essentially hidden, if you will. It's some construct thing that we think of, but it's not observable. They're said to better represent research constructs than actual measured variables because they contain less measurement error, because they can't really be measured. So some examples of latent variables are intelligence, confidence, self-esteem, and physical condition. So there are variables that we use to measure these constructs, but the constructs in and of themselves are not measurable. On the other hand, observed variables are directly observable or measured and recorded. They're data that actually exist in your data files. So these are the variables that are used to define or infer the latent variables. So some examples of these are risk scores that we use to infer intelligence, gender, scale data that we may use to infer confidence or self-esteem or quality of life, weight, height, measurements that we may use to infer physical condition. We also talk about endogenous and exogenous variables. So endogenous variables are similar to dependent variables. So the value is determined by other variables within your system. And exogenous variables are similar to independent variables, where the value is not affected by other variables in the system. Now, they're most likely impacted by variables outside of the system, but not those within. So in SEM, it's important to note that a variable can actually be endogenous and exogenous, or if you like to think about it, independent and dependent. And then when we look at recursiveness, a recursive model is one where all of the causal effects are unidirectional and the disturbances are uncorrelated. And a non-recursive model contains one or more feedback loops or reciprocal effects. All right, so that's all my terms. And I know that's super fun stuff, but I think it's important because I'll be throwing these terms out later that we just kind of go over them. So SEM is kind of known as a couple of other analyses. It's sometimes called or known as covariant structured analysis, analysis of moment structures, analysis of linear structural relationships, which is also LISRL, and then occasionally causal modeling. But we have to take caution when interpreting SEM results as causal, because the requirements to determine causality are not likely to be satisfied within the structural equation modeling. Thus, we can't really determine causality. Rather, we can make causal inferences. All right, so what is the goal of SEM? It's to determine the extent to which the theoretical model is supported by sample data. If the sample data support the theoretical model, then more complex theoretical models can be hypothesized. If the sample data do not support the theoretical model, then the original model can be modified. So it's kind of like building a set of Legos. And so you build a set and then you test, is that the way that you want it? If it is, then you can continue to build on it and further refine it. And if it's not, then you kind of can modify and start over. So there are a lot of questions that can be addressed using structural equation modeling. The main question asked is, does the model produce an estimated population covariance matrix that's consistent with the sample or observed covariance matrix? After we assess whether or not our model is essentially a good fit, then we're going to look at, is the model adequate? So parameters are estimated to create an estimated population covariance matrix. So if the model's good, then the estimates will produce an estimated matrix that's close to the sample covariance matrix. When I'm talking about matrix, think of your correlation matrix. That's what we're talking about. So it's like this big grid of interrelationship. So this is evaluated primarily with your chi-square test statistic and fit indices. So you're evaluating your adequacy using your fit indices. Another question we look at is which model is best. So kind of like I said, you've got these Lego models. You have different models, and each model or theory generates its own covariance matrix. And so models representing competing theories in a specific research area are then estimated. So you may have multiple models that are compared against each other and then are evaluated. Another question that is addressed is how much variance in the variable is accounted for by the factors. This is kind of a big question, right? So the answer SEM provides is through R-squared type statistics. So when you run your SEM, you're going to get an R-squared type statistic. It's going to give you your variance accountabilities. The next question is how reliable are each of the measured variables? So SEM derives the reliability of measured variables and internal consistency measures of reliability. So you're going to get those reliability measures in your output as well. Another question is, are some paths better at predicting the outcome? So we're going to look here in a little bit at some models, and you're going to see there's multiple paths, and we want to know, are some of the paths better at predicting the outcome than others? So SEM generates some parameter estimates, or coefficients, if you will, for each path in the model. We can use those to distinguish if one of those paths is more or less important than the other in predicting the outcome. Another question that we're going to look at is the relationship direct or is it a mediated? In other words, does the independent variable affect a specific dependent variable, or does the independent variable affect the dependent variable through a mediating variable? Another question is, do two or more groups differ in their covariance matrices, regression coefficients, or means? And here we're going to use multiple group modeling in SEM to test these group differences. Finally, we're going to look at, are there differences across time? So differences across time using repeating measures can be examined through time intervals analysis. And this can be, that time interval could be years, days, months, seconds, microseconds, doesn't really matter. If it's a time interval and repeated, we definitely have ways in SEM to evaluate those models. And finally, you can actually use SEM to look at some multi-level modeling where you have different nested levels of measurement. I'm not really going to go into that in this talk. So let's talk about why SEM. Why would we want to use a structural equation modeling? So if we have a need to look at multiple observed variables, then we may want to look at SEM because it permits complex phenomena to be statistically modeled and tested. That means we can look at multiple group SEM models. Let's say we're collecting educational data at more than one level. So we're looking at students, teachers, schools. We're looking at patients, doctors' offices, hospitals. We can put these more complex models in and evaluate them. And regression estimates are better accounting for your error when you're looking at these complex models and when you're using SEM. So you also have greater recognition that's given to the validity and reliability of the observed scores. Again, because SEM takes measurement error into account when it's analyzing the data. All right, so what kind of research is appropriate for SEM? If we have research where the key constructs are complex and multifaceted, and we may want to look at SEM. If the research specifies systems of relationships, it might be appropriate for SEM. And then research with a focus on mediated effects on variables might be appropriate as well. There are currently quite a few software programs that are available to use for SEM. So AMOS is one of the, AMOS and Listral are really kind of one of the first, but AMOS, which is now an IBM product, EQS, Listral, M+, R has a package for SEM, Alice, MX, CPAS, Stata, Tetrad. There's a number of software programs that are currently available, and they each have their tweaks, as do most stats packages. So how is SEM used? So SEM analyzes the variance covariance matrix of variables, not the raw data. So to conduct the analyses, both a structural and a measurement model is designed. And the structural model refers to relationships among the latent variables that allows one to determine their degree of correlation. And each structural equation coefficient is computed while all other variances are accounted for. So the coefficients are calculated simultaneously for all endogenous variables rather than sequentially. The measurement model actually looks at the latent variables and the observed variables and error variables within that system. So we'll take a closer look at that here in a second. So there are quite a few theoretical models that are tested in SEM: regression, confirmatory factor analysis, confirmatory composite analysis, path analysis, multi-group modeling, longitudinal modeling, partial least squares path modeling, latent group modeling, and then hierarchical and multilevel modeling. It's quite complex. So before using SEM, there are some things that we have to consider. SEM can be used in either cross-sectional or longitudinal studies, and these models often include autoregressive effects where a variable that's measured at 2 time points is correlated with itself. So this corrects for an overestimation of the variables among exogenous and endogenous variables. SEM can be used with continuous and binary data, and it's able to manage both data types simultaneously. And then it can be employed for both exploratory and confirmatory models. In the exploratory model, all the latent variables are assumed to influence all of the observed variables so that the number of latent variables are not predetermined, and the measurement areas are not allowed to correlate. Although exploratory and confirmatory analyses are subsets of SEM involving the measurement mirror only, really CFI is the one that's more frequently used to test the hypothetical constructs. This is really, if I haven't said it, it's really grounded in theory very strongly. All right, so now we're actually going to look at some models. And before we do, I just put up a slide with some common path diagram symbols. So your latent variables are traditionally represented in either a circle or an oval. Observed variables is either a square or a rectangle. Unidirectional path is an arrow, and it's either straight or could be crooked. Recursive non-reciprocal relationship between variables is also a single arrow. Your error variables, when you have error on a latent variable, is just going to be a circle or an oval, and with a little arrow pointing to your variables. Same if you're looking at measurement error in your observed variables, it's just a little circle up top. When you look at your correlation between variables, it's either going to be a two-sided arrow or it could be a two-sided curved arrow. And then your non-recursive, which are your reciprocal relationship between variables, are going to be two arrows pointing opposite of each other. So those are the common path symbols that we're going to use. So let's take a look at a model, and we're going to kind of build this model on itself. So in SEM diagrams, latent variables are commonly shown as ovals. So I said in path, it could be ovals or circles. In SEM, commonly they're shown as ovals, and observed variables are rectangles. So an arrow is drawn from the latent variable to each of the observed indicator variables for which the factor loading is going to be computed. The unique measurement error is noted by the little circle with an E for error. This indicates that some portion of each observed variable is measuring something other than the hypothesized latent variable. And then the curved arrow between two variables indicates that the variables are correlated. So in this model, I just threw that correlation on the errors. So let's say you were using subscales of a larger scale, then you know that those subscales are going to have some correlation. So you would have curved arrows between those. To determine the magnitude of coefficients, then the researcher is going to specify the structure of the model. So here, the researcher may expect that there's a correlation between your latent variables eta 1 and eta 2, as shown by the double-headed arrow. There may not be an expected relationship between eta 1 and eta 3, so there's no arrow drawn. And finally, the researcher may hypothesize that there's a unidirectional relationship of eta 3 and eta 2. So there's an arrow pointing from eta 3 to eta 2. All right, this is our basic model. Now we're going to overlay the structural model. And the relationships among the latent variables eta 1, eta 2, and eta 3 represent the structural model. The researcher details these relationships by writing a series of equations, and the combination of the equations specify the pattern of relationships. So this is our structure, looking just at your latent variables. Now, when we add in our measurement models, you can see that this is the second component, and it consists of the measured variables, so variables, the rectangles variables 1 through 7, as well as latent variables, your ovals eta 1 through 3. And for this measurement model, 1 depicts eta 1, which is the construct underlying measurement variables 1 and 2. All right, how do we get there? So let's talk about how to conduct an SEM. Using previous research and theory, we want to develop hypotheses about the relationship amongst the variables. These can be either direct or indirect, which are mediating, and unidirectional or bidirectional, as we saw earlier. Care must be taken in using variables that provide a valid and reliable indicator of the constructs under study. So next, we're going to outline the model. So now that we have our hypotheses, we outline the model, and we're going to do that using a path diagram depicting the structural and measurement models, as you saw previously. We must determine the number and relationships between measured and latent variables and whether or not they're included in our model. And we must also remember that all measurements are made with error. In the second step, we're going to identify the model. So for each unknown parameter in the model to be estimated, there must be enough known pieces of information. So that's variance and covariance variable values. And there are different levels of identification. So models can be under-identified. An under-identified model has fewer known parameters than unknowns, and it's virtually impossible to solve this mathematically. An underdefined identified model, there are an infinite number of solutions, and therefore there's no unique one. And so the problems can be remedied with the addition of independent variables, which require that the model is conceptualized before you start data collection. When you have just identified models, you have an equal number of known and unknown parameters. And then when you have an over-identified model, you have more knowns than unknowns. While both identified models, just identified models, and over-identified models are considered to be identified models, over-identified models yield a likelihood value which can be used to assess model fit. So there's several ways to identify your model. One way is to assess the identification status using your software. So it's going to, in the output, give you an identification status. You can also compute the identification quickly by hand using this brief formula. So let S be the number of observed variables in the model. And the formula 1/2 S times S plus 1 is the number of non-redundant parameters. And T is the number of parameters to be estimated. So if T, the number of parameters to be estimated, is greater than the number of non-redundant parameters or observed parameters, then the model is unidentified. If the number of parameters to be estimated is less than the number of known parameters, then the model is over-identified. Short and sweet. In the third step, we're going to estimate the model. So there are many estimation procedures available to test models. Maximum likelihood is set as the default in most of the SEM software. And maximum likelihood is an iterative process that estimates the extent to which the model predicts the values of sample covariance matrix, with values closer to 0 indicating a better fit. So the name maximum likelihood is based on its calculation, in that the estimate maximizes the likelihood that the data were drawn from its population. So these estimates require large sample sizes. They don't usually depend on the measurement units of the measured variables. It's robust to non-normal data distributions, and it's unbiased and efficient. Not a very good fit if the variables in the data set are not continuous or binary. Another widely used estimate is least squares, which minimizes the sum of the squares of the residuals in the model. So least squares is similar to maximum likelihood in that it estimates patterns of relationships, but it does so by determining the optimum solution of minimizing the sum of the squared deviation scores between the hypothesized and the observed model. It does sometimes perform, well, I should say often performs better with small sample sizes, and provides more accurate estimate of the model when the assumptions of distribution, independence, and asymptotic samples are violated. And then the third model, ADF, or estimation procedure, ADF, is also known as weighted least squares. It's less often used, but it could be appropriate if the data are skewed or peaked. This method actually requires large sample sizes of 2 to 500. So it's not as frequently used. After estimating the model, we're going to determine the model's goodness of fit. The estimation procedure determines how well the model fits the data. Fitting the latent variable path model involves minimizing the difference between the sample covariances and the covariances predicted by the model. The estimation can be classified by type of distribution. So maybe it's multinomial, maybe it's elliptical, maybe it's arbitrary, and attempts to represent the population covariance matrix in the sample variables. So it's going to attempt to represent your population. Then an estimation procedure is selected, which runs through an iterative process until the best solution is found. A good fit is represented by low residual values. So like you want to get to 0.00, which is kind of perfect fit, which represents the amount of variance not accounted for by the model. To determine the model's goodness of fit, sample size is really important consideration. So it has to be large enough to obtain a stable estimate of parameters. General guidelines are going to suggest that you need 100 to 200 cases in order to obtain stable results. So our final step in our SEM is to re-specify the model if necessary. So to obtain improved fit results, the sequence of steps is repeated until the most succinct model is obtained. To improve the model estimations, you can examine the size of the standard residual values between variables. So large residuals may suggest an inadequate model fit. You can remedy this by adding a path link or including a mediating or moderating variable, if of course that's theoretically supported. Once the model is recalculated, its fit may show improvement and the residual may be reduced. These results then need to be confirmed on a different sample. And the replication strengthens confidence in the intervals and provides implications for theoretical development and practical application. So let's look at a real world example. So this example comes from psychiatry, where the investigators were looking to understand patient experiences in schizophrenia. Lomberg and colleagues examined the role of positive symptoms and duration of schizophrenia on dichotic listening of patients. The dichotic listening test is a simple, non-invasive behavioral technique that's used as a means of assessing the functional integrity of the left temporal lobe language areas. Previous research has suggested that individuals with a number of positive symptoms of schizophrenia showed an increased impairment in left temporal lobe language processing. So Loberg et al. Attempted to evaluate the relative contribution of positive symptoms and duration of illness as predictors of dichotic listening performance, using both attention and laterality components. Their sample consisted of a total of 129 patients. So they used the positive and negative syndrome scale and the extended brief psychiatric rating scale as their symptom ratings. They included hallucinations, thought disorder, and unusual thought items from the symptom scales as variables in the SEM. The duration of the disease was calculated as the age of testing minus the age of onset. Dichotic listening was measured by patient responses to consonant and vowel blends spoken through headphones. And in one condition, patients were told which ear to listen with, attention, and in another, they were not, laterality. So the analysis of the model using SEM indicated that the model fit the data well. What we don't see in the diagram is that the CFI, the confirmatory factory index, was 0.986 based on 11 degrees of freedom. So the positive symptoms were measured by hallucinations, disorganized thoughts, and unusual thought content. Dichotic listening was measured by accuracy of sounds identified in each ear according to the condition in which the patients heard the sounds. You can see in the model that all the path coefficients to the predicted latent variables are moderate to high. They range from 0.32 on between attention component and forced right ear to 0.87, which is that relationship between positive symptoms and unusual thought content. In presenting their results, the investigators determined the relationship between dichotic listening and schizophrenia, duration of schizophrenia, and number of positive symptoms were related to the accuracy of sound detection. These results supported findings from previous research suggesting impaired language processing and structural abnormalities in the left superior temporal gyrus for patients with schizophrenia. The model also suggested that patients with many positive symptoms were likely to have difficulty identifying sounds accurately, especially if the duration of the illness is long. Because this is a cross-sectional model, it's not really known whether the language processing deficit existed before, at the same time, or after that onset of schizophrenia. Direction of the cause in the model is unknown. But given that time was an important variable in the model, we can explore the advantages of longitudinal modeling or measuring variables at more than one time point. That is, using the same measures of positive symptoms of schizophrenia and language processing taken at time 1 and time 2, path coefficients between the two latent variables at both points in time can be simultaneously examined to determine those that are significant. Previously, a cross-flag design would have been used whereby positive symptoms at time 1 are correlated with language processing at time 2. This correlation has been compared to the correlation between language processing at time 1 and positive symptoms at time 2. This comparison does not account for autoregression, does not include latent variables, and cannot be easily applied to multiple time points or multiple variables. So an alternate method is multiple regression analysis, where the positive symptoms of schizophrenia and language processing measured at time 1 are used to predict language processing at time 2. The magnitude of the regression weights would indicate the strength of the relationship between schizophrenia and language processing while controlling for initial language processing. Although this takes autoregression into account and includes multiple measured variables, Latent variables cannot be used, and reciprocal patterns, the impact of language processing on positive symptoms, cannot be estimated. This is why the investigators determined that SEM was the best course of action. So in Model 1A, the one that we were just looking at, both positive symptoms and duration were defined as directly contributing to both dichotic listening components. This yielded an acceptable fit. Next, the contribution of duration on the dichotic listening laterality component was deleted based on a low and non-significant path coefficient. This created a second model, which also showed an acceptable fit. That model was not presented in the manuscript but merely mentioned. The overall fit of the model did not change significantly compared with the previous model. Finally, the contribution of positive symptoms on the dichotic listening attention component was deleted. And so you can see that that latent variable is missing. This created the model that you're seeing now. Again, the overall fit of the model did not change significantly compared to the previous model. In this model, both the remaining prediction path coefficients were strong and significant, indicating no need for further trimming of the model. Further, the fit indices indicated that the model showed good fit in the data. Based on the principle of parsimony, it could be concluded that this model was the model with the best fit. And ultimately, this is the model that the investigators went with. So these are two of the tables from the manuscript to show how they represented, outside of their models, the results of their analyses. So the first two tables were essentially descriptive and correlations they ran prior to running an SEM. So in table 3, they represented intercorrelations between predictor variables included in the SEM. So we all recognize the correlation table. And then in table 4, they presented descriptive statistics for the variables that were included in the SEM. So what are the advantages of using SEM? Well, it allows researchers to specify more complex models. Using SEM, you can test hypotheses based on multiple constructs that may be indirectly or directly related for both linear and nonlinear models. It's distinguished from other types of analyses in its ability to examine many relationships while simultaneously parceling out measurement error. It can also examine correlated measurement error to determine what degree unknown factors influence shared error among variables, which may affect the estimated parameters of the model. It also handles missing data really well by fitting raw data instead of summary statistics. It can be used to manage longitudinal designs such as time series and growth models. And it has greater statistical power than multiple regression. It can test whether or not the model is consistent with data in ways that we cannot in a standard regression model. So there are some disadvantages and criticisms as well. As with any method, SEM has its limitations. Although latent variable is a closer approximation of a construct than is a measured variable, it may not be the pure representation of the construct. Its variance may consist of, in addition to true variance of the measured variables, shared error between the measured variables. Also, the advantage of simultaneous examination of multiple variables may be offset by the requirement for larger sample sizes for additional variables to derive a solution to the calculations. SEM cannot correct for weaknesses inherent in any type of study. Exploration of relationships among variables without a priori specification may result in statistical significance but have little theoretical significance. In addition, poor research planning, unreliable and invalid data, lack of theoretical guidance, and overinterpretation of causal relationships can result in misleading conclusions, which is fairly applicable amongst most methods. So I went through that really, really quickly. These are the citations that I used, and also a resource. I don't know if you all are familiar with the National Center for Research Methods. Dr. Sturgis is the director. They have a ton of online courses for statistical models, techniques, and just some really, really helpful and good information. And then I did pull out, I showed Robert and Chris my book from school. I pulled it out. It's really old, but Dr. Shoemaker and Dr. Lomax have a beginner's guide to structural equation modeling that is that's really helpful as well. All right, that is the end of my presentation. I'm going to take questions that I may or may not be able to answer because it's been quite a while since I've actually run an SEM.
Lori, is this done by a team of statisticians, or can this be done, I mean, using the software, or does it take a team effort? Because there's a lot going on here.
There is. It's pretty complicated. No, it definitely can be done by a single statistician. The most complex part, honestly, is developing your models, right? So looking at what's out there and determining your theories. Once the model's developed, the actual analyses are pretty easy to compute in the software.